So if you're using generative AI these days, you probably know that feeling, right? That cycle of,
Yeah.
well, frustration.
Yeah.
1 minute, it's amazing. It's like this brilliant partner writing code, giving you insights.
Uh-huh.
And the next, it's just confidently making stuff up, or it gets stuck repeating itself, or maybe completely forgets the main thing you told it 5 minutes ago.
That exact problem, that kind of maddening inconsistency,
Yeah,
that's really what we're digging into today. We've been looking at this technical lecture, and it makes a pretty bold claim
which is,
that most of this frustration, it's actually self-inflicted,
yeah,
and it basically comes down to a naming problem.
a naming problem. How so? The source material says calling these things artificial intelligence is responsible for, what, 50% of deployment bottlenecks? That seems huge.
It is huge, but think about it. We hear AI, and we expect, general intelligence, real reasoning, deduction. But the machine isn't built for that. So the big mindset shift we need, the key to actually mastering these tools, is to stop thinking sentient AI and start using its proper technical name.
Which the lecture defines as
Predicting the next word, probability computer.
a predicting the next word probability computer. That's specific.
It is. And that name really sets the boundaries. It tells you exactly what it can do, and maybe more importantly, what it can't.
All right, let's unpack that. The probability computer. Now, we're not aiming to turn you listening into ML engineers or anything,
Definitely not.
but understanding the basics of the architecture seems pretty key to getting why it has these limits. The analogy in the source was good. You don't need to build a car, but knowing it runs on the ground stops you expecting it to fly.
Exactly. And the architecture that keeps these things on the ground is called the transformer. It's the backbone, really, for all the big names you hear, GPT, Llama, Gemini, all of them.
And specifically, we need to look inside the decoder part. That's the bit doing the actual writing.
That's the engine, yeah. The part that generates the text output.
Okay, so let's imagine we type in a prompt, something a bit controversial maybe, like, is Elon Musk a moron? What happens inside the machine?
Right. First step. Your sentence gets chopped up into individual tokens. Think of them mostly as words or sometimes pieces of words.
Okay, tokens.
Now, when these tokens first enter the system, they're kind of isolated. Each one only knows two things initially. First, its own background knowledge, everything it learned during training, like Musk is a person, he's wealthy, associated with Tesla, SpaceX, that kind of thing.
And the second thing?
Just its position in the sentence you just typed. That's it. They don't know about each other yet.
Feels a bit like strangers at a party.
Yeah. The source calls the next step the team icebreaker, which is actually pretty fitting. It's technically called multi-head attention.
Multi-head attention, okay.
This is where the system forces those tokens to look around, basically, to interact and figure out how they relate to each other right now in this sentence. So Musk realizes it's the subject, and moron seems to be describing it based on grammar and the immediate context.
Got it. They
Yeah.
figure out their roles in the sentence. What's next?
After the icebreaker, they move into something called the feed-forward network. The lecture called this closed-door cultivation.
Closed-door cultivation. Sounds intense.
It kind of is. This is where each token, now aware of its neighbors and its role, does some internal refining. It processes the context it just gathered and figures out its deeper meaning in this specific situation. This is the real computational heavy lifting part, calculating all the possibilities.
Okay, so after all that internal calculation, how does it actually pick the next word?
It generates a massive probability table, literally a list of all the words it knows, each with a score saying how likely it is to come next. From our is Elon Musk a moron question, maybe yes gets a 50% probability and no gets 40%.
50. 40, okay, that's close.
Right, and here's the crucial bit. The so-called intelligence pretty much stops right there. The model uses a surprisingly simple, purely linear algorithm to pick the next word.
A linear algorithm, like just picks the highest score.
Well, that's one option. If you set it to always pick the absolute highest probability word, you get very consistent but often very rigid, maybe kind of deadpan answers.
Right, no creativity.
Exactly. So the other option is to tell it, okay, pick randomly from, say, the top words that add up to 90% probability. This introduces variety, elasticity, makes it sound more creative.
But it also makes it less predictable, more unstable.
Precisely. That's the fundamental trade-off baked into the system, imagination versus rigor. You're always balancing those two.
And hang on, that linear selection, choosing between that 50% yes and 40% no, That sounds like the root cause of hallucination, doesn't it?
Absolutely. It connects directly. If the model internally calculates, 50% chance it's yes and 40% it's no, it hasn't actually determined the truth. It's basically holding contradictory ideas with different weights.
But I have to give an answer.
It has to produce a word.
Yeah.
So between that 50% and 40%, it effectively flips a coin. It makes a random choice based on those probabilities.
Yeah. Wait, really? This incredibly complex multi-billion-dollar system essentially performs a high-stakes coin toss when it's unsure.
In essence, yes. And what's worse is what happens after the coin toss.
Okay.
The source calls it the danger of conviction. Once it randomly lands on, say, yes, the way these models work, this self-regressive process means every single word it generates after that is laser-focused on aggressively proving that initial randomly chosen yes.
Oh, wow. So it doesn't just make a random guess, it doubles down and starts building a whole argument for it, even if the foundation is just chance.
Exactly. It leads to incredibly confident-sounding but potentially completely fabricated or biased answers,
Yeah.
all built on that initial probabilistic guess.
That feels fundamentally flawed if you're aiming for truth. Which makes you wonder, isn't there a better way? Can this be fixed? This source mentioned something Meta tried, right? Continuous chain of thought.
Yes.
But it got banned.
Yeah, it's a fascinating story. Meta's idea was trying to solve that exact coin toss problem. They thought, okay, instead of forcing the model to pick between 50% and 40% right at the start of its internal thought process.
Just thought chain, yeah.
Right. Why not let it hold on to that contradiction? Let it keep both possibilities weighted in mind, like maintain a kind of quantum superposition state throughout its entire internal reasoning.
Whoa. So it would sort of explore both sides of the argument internally, keeping track of the probabilities.
Precisely. The thinking process could become much more objective, carrying all the weighted options right up until the final moment when it has to give an answer. Then the superposition would collapse into the most statistically reasoned conclusion.
That sounds amazing for accuracy. Why on earth would it be banned?
Well, think about the implications for training and safety. If the model is maintaining this complex, contradictory state internally, its reasoning process becomes completely opaque to us. Utterly untraceable, a true black box.
Ah, so you can't see how it reached the conclusion anymore.
Exactly. And the big players, OpenAI, Google, Anthropic, the rest, they push back hard, citing safety concerns, the inability to monitor or understand the AI's thoughts. The industry effectively blocked it. So we're back to the linear coin toss mechanism. We're stuck managing the randomness.
Okay, so first big takeaway. It's a probability computer, prone to random guesses because of a fundamental design choice, partly driven by safety concerns. Now, what about the second major limitation you mentioned? The memory thing.
Right. This is the other really critical piece of the puzzle. LLMs have absolutely no memory. Zero. Zip. Nada.
None. That can't be right. I chat with these things and they remember my name or details I mentioned earlier in the conversation.
Yes. That feels like memory, but it's actually a clever engineering trick. The source calls it the cheat sheet.
The cheat sheet.
Yeah. What's happening is that the platform, the engineers behind the chat interface, are invisibly adding hidden instructions to every single prompt you send.
Every time.
Every single time. So you just type, summarize our meeting, but what the model actually receives might be something like, system note. User's name is Sarah, she works in marketing, prefers a semi-formal tone. Previous topic was budget allocation. User now says, summarize our meeting, respond helpfully.
Wow. Okay, so there's a hidden post-it note reminding the model who I am and what we were just talking about.
Exactly. It's short-term artificial memory bolted onto the side. It's not inherent to the model itself. The only true memory the model has is the knowledge baked into its parameters during that massive initial training phase. Every chat is, to the core model, the very first time it's ever encountered you.
And this cheat sheet, this injected context, it has limits, right? That's the context window.
Precisely. The context window is the maximum amount of text your prompt. Plus that hidden cheat sheet, the model can actually see or process at one time. Think of it like its active attention span.
And if the conversation gets long, that window fills up.
It fills up fast. And the system has to do something with the older information to make room for the new stuff. The common approach is compression.
It summarizes the earlier parts of the chat.
Yeah, it tries to summarize the older dialogue, but compression is lossy. Important details, nuances, maybe those strict rules you gave it at the start of a project, they get diluted, summarized away.
Ah, so that's why it sometimes forgets instructions or the core point after a long back and forth. The critical info got compressed and squeezed out of the window.
That's usually what's happening. That dilution is a major cause of quality degradation in long conversations.
Okay, but compression sounds problematic for businesses, right?
Yeah.
If you need an AI to understand, say, millions of internal documents, you can't just summarize them all down.
Absolutely not. Compression fails completely at that scale. That's where a different technique comes in called retrieval augmented generation, or RAG.
Retrieval augmented generation.
With RAG, instead of trying to stuff summaries into the context window, the system does something smarter. When you ask a question, it first goes and searches a huge database, like all your company documents, finds the most relevant few paragraphs or snippets related to your query, and then it feeds only those relevant snippets into the context window along with your question right before the model generates an answer.
So the model always gets fresh, highly relevant, precise information for each specific query without relying on potentially lossy summaries of the entire database.
Exactly. It bypasses the dilution problem by retrieving just what's needed, just in time.
Right.
It's a much more scalable approach for large knowledge bases.
Okay, this is making sense. So recap, it's a probability computer, not truly intelligent, and it has no real memory, only this managed context in the window, sometimes supplemented by OG. What does this mean for us practically? How do we use this knowledge?
It means we absolutely have to ditch the idea that we're talking to an oracle or, a wish-granting well.
Right.
Every word we feed it is a constraint. It's programming. We are literally using human language to program the probability computer.
Programming the probability. Okay, give me an example, like the Myanmar capital one from the source.
Perfect example. If you just ask, what is the capital of Myanmar? That's actually a poor prompt.
Why?
Because the capital changed, right? From Yangon to Naypyidaw back in 2005. The model's training data has tons of text mentioning both cities as the capital. So the probabilities for both answers are likely quite high, maybe close.
Leading to another potential coin toss, hallucination territory.
Exactly. But if you program it better, if you add a constraint like, what is the capital of Myanmar now?
The word now.
That single word acts as a powerful constraint. It forces the probability calculation to heavily favor the information associated with the current time, pushing Naypyidaw's probability way up and Yangon's way down. You've guided the probability towards the correct, rigorous answer.
So it's about adding those crucial constraining words. That also explains the weird issue with AI image generators struggling to draw hands with 5 fingers, doesn't it?
It does. It's not that the AI doesn't know humans have 5 fingers. It's a data problem, as the lecture pointed out. Think about the trillions of images it trained on. How many show a perfectly clear, unobstructed hand with exactly 5 fingers fully visible?
Probably not that many, actually. Hands are often holding things or at weird angles or partially obscured.
Right. So the probability computer lacks enough clean, unambiguous examples of 5-fingered hand in its visual training data. It makes that specific constraint hard to satisfy reliably. It's a failure of data, not common sense.
Okay, this is all leading somewhere practical. The source material suggests that basically all problems we have with these AI applications, whether it's just getting a chatbot to follow instructions or deploying complex industrial AI, they boil down to 2 key questions.
That's the core diagnostic tool, yeah. The 2 soul-searching questions, as the lecturer put it. Number 1, did we choose the right model? Meaning, are we using a general-purpose chatbot for a task that really needs a specialized, fine-tuned model? Like using ChatGPT for complex medical diagnosis probably isn't the right model choice. You'd want something trained specifically on medical data.
Okay, choose the right tool for the job. Makes sense. And the second question.
Number 2, did we provide the right context?
Back to the context window and RAG.
Exactly. Are we making sure the absolutely critical information, the constraints, the rules, the necessary background knowledge is actually in the context window when the model generates its response?
Yeah.
Either by putting it in the prompt directly, managing the conversation history, or using RAG effectively.
Right model, right context. It sounds simple, but I can see how almost any issue could trace back to one or both of those.
It covers a surprising amount of ground.
This also ties into that whole debate around AI agents, right? The idea of AIs acting autonomously. OpenAI pushes agents, but the analysis seemed to favor Anthropic's framing.
Yeah, the preference was for Anthropic's term agentic. It's a subtle but important difference. Agentic refers to how much decision-making power or autonomy you choose to give the AI.
as opposed to assuming full autonomy from the start.
Right. And the argument is, given the inherent probabilistic nature and the potential for instability we've discussed, for most critical tasks today, prioritizing stability and control is paramount. You simply can't give this probability computer too much unsupervised freedom if you need reliable, predictable output. It's a direct trade-off with the current transformer architecture.
Okay, so let's try and synthesize this. We've covered a lot.
Mhm.
If you want to use these LLMs well, avoid that cycle of frustration. What are the absolute core truths to internalize?
I think it boils down to three main things. First, forget intelligence. Think tool. It's a powerful tool, but it's not thinking like we do.
Okay, tool, not intelligence. Second,
Second, it operates on probability, not truth. Its goal is to predict the next most likely word, not necessarily the most factual one, unless you constrain it properly.
probability, not truth.
Mm.
Got it. And third,
Third, it has no memory, only context. That memory you perceive is the engineered cheat sheet living within the limits of the context window, possibly helped by our day.
tool, probability, context. Not intelligence, truth, memory.
That's the core mindset shift, and the final analogy from the lecture really drives it home.
The car versus airplane one.
Yeah. The invention of the automobile was obviously world-changing, speed, efficiency, connecting people. But imagine if, when it was invented, everyone was told it was an airplane.
They just keep trying to make it fly, pushing it off cliffs.
Exactly. Leading to nothing but frustration, disappointment, and probably a lot of broken axles. They'd curse the machine for failing at something it was never designed to do.
But by understanding it's a car, the most powerful, fastest, most tireless car ever built, but still fundamentally ground-based, then you can figure out how to use it properly. Build roads, infrastructure, use it to revolutionize transport, drive progress.
That's the point. Understand the LLM for what it is, an incredibly powerful probability computer, a ground-based vehicle for information, and you can use it effectively, rather than cursing it for not being the magical flying intelligence we might have initially wished for.
So, the challenge for everyone listening, the takeaway action.
Apply those two soul questions next time you interact with an LLM. Before you hit send on your prompt, just take a second. Ask yourself, one, am I using the right model for this task? And two, critically, have I given it enough context? Have I programmed the probability computer with enough constraints to guide it towards the rigorous, truthful answer I need?
Or are you just leaving it up to that coin toss?
Are you leaving it up to the coin toss? That's the question.